We'll review for exam 3. And using the review document, I picked out the ones that I want to be sure and cover. And if you've run across any that give you particular trouble, then you can stop me now, or if it comes to mind, just raise your hand and we'll stop and do yours, because I don't want to leave anybody's questions unanswered, just so I can finish my blurbs. All right. And after this, we're going to do our lab, freezing point depression. So you'll need a copy of that if you don't already have one. I got some extras up here. All right, number 1. Which of the following groupings are 3 terms closely related? Okay, let's see what the terms are. Kinetic energy, potential energy. Okay, I see those two. Energy of motion. Energy of motion, that's kinetic energy. Cohesive force. Which one is cohesive force? That one right there. Right. When potential energy is high, you have high cohesive force. Potential energy of attraction, that's this one. What else we got? Disruptive forces, that's this one. Disruptive forces. Potential energy, energy of attraction, disruptive. Electrostatic interaction. That could be either one. Okay, disruptive, potential, electrostatic, cohesive. Okay. Well, no, actually potential energy, remember the different types of potential energy we have, but that we studied. You have positional potential energy, like if I get on top of the building, I had to add energy and I've stored energy in my position. And then how do I get it back? Jump off the building, right? When I hit the ground, I get all that energy back. But you can also have energy stored in chemical bonds. You can have energy stored in things like rubber bands. And that's how I think of electrostatic attraction. It's like a rubber band. If you have a positive and negative charge, and then you try to pull them apart, then you have to add energy to get them apart. And then when you release them, they snap back together. So yeah, this electrostatic is part of the potential energy domain. So which ones go together? Well, let's see. Kinetic, A and C have kinetic, but C has electrostatic, so that one doesn't do. Disruptive is fine, but electrostatic is not. How about A? Energy of motion, cohesive force. That's not a cohesive force. This is. All right, so we can throw A and C out. B and D have potential energy, energy of attraction potential. Okay. Disruptive for B, no. Disruptive belongs here. All right, so process of elimination says D should be the answer. Potential energy, electrostatic interaction, cohesive forces. Those belong together. All right. Number 2. The phrases, particles close together and held in fixed positions, completely fills the container, apply respectively to. Right. We're talking about the phases, and they're 2 different phases. You can tell because with particles close together and held in fixed positions, they can't expand to fill the container. So that's definitely 2 different phases. The first phase should be a solid. Everything's in fixed position. Completely fills the container. The only one that does that is a gas. Right? Liquids, not even liquids, will completely fill the container. So let's see, B, solids and gases. That works. How about 3? How many times larger in size is the atmosphere pressure unit than the millimeter mercury pressure unit? All right, if we say 1 atmosphere, what is that in terms of millimeters of mercury? 760. Oops. Try that again. Millimeters of mercury in terms of pressure units. All right, remember what I said, if the unit gets bigger, the number gets smaller. Vice versa. If the number gets bigger, the unit is smaller. So the ratio between the two is the size of this difference, this number ratio. So this unit of measure is 760 times smaller than that one, or this unit is 760 times bigger than that one. Okay, that's why C is the answer. The ratio is 760. It works better. Charles' law. Remember which one Charles' law is? What two gas parameters are related in Charles' law? Volume and temperature, which means pressure and moles must be constant. Okay, so how are these two related? Are they directly proportional or inversely proportional? If you increase the temperature, what's going to happen to the volume? Everybody, wakey, wakey. Anybody out there? That's the simplest expression of Charles' law. So how does that fit here? Let's see. At constant pressure, the volume of a gas sample is directly proportional to its temperature in Kelvin. So that would be B. Okay. This kind of weather makes everybody sleepy, doesn't it? Don't worry, you'll get your hour back this weekend. Five. The correct formula equation for the ideal gas law. What do we normally see when the gas law is written? We normally see it in a linear fashion. Like that. Do we have that one in there? Yeah, first one, A. Don't have to rearrange it to find it to match something. Pressure, volume, moles, temperature, gas constant. What's the volume in liters occupied by 2.12 moles of nitrogen gas at 0.745 atmosphere pressure and a temperature of 55 degrees? All right, for the gas laws and the gas problems, which one is this? Before, after, or state? Are you given 2 of anything in there? 2 of any units? No. They're all moles is separate, is not repeated. Atmosphere pressure is not repeated. Temperature is not repeated. That means you have to use a state function, which is the ideal gas equation. All right, so the best way to keep from messing up is to put what you know in a table. Temperature, volume, pressure, moles. So the temperature is 55. We know we're going to have to change that one. All right, so that's 328. Okay. Yep. Volume needs to be in what units? Oh, that's the question. Okay. Pressure. Atmospheres? Yes. Notice I preceded that with a 0. And then moles. So it appears that all of these are in the correct units. Now, that one's K, atmosphere is moles. So when we use this equation, R, let's solve for volume first. Volume equals nRT over P. Moles, I'm going to leave the units out so I don't have to use up all my room. That's the constant you use with those units of measure. Temperature and pressure. 745. So if we do our math correctly, we should end up with 76.6 liters. Okay. Number 7, scroll. The partial pressure of helium in a gas mixture of helium and nitrogen trifluoride is the partial pressure of helium in a mixture of nitrogen trifluoride, both gases. So we're looking at the partial pressure of each one. According to Dalton's law of partial pressure, that should be a total. If those are the only two gases in there, partial pressure of each one added up gives you the total pressure. But let's see, we got to figure out which one of these is correct. A says the pressure that helium would exert in the absence of yeah, that's what partial pressure means. That's the contribution of helium to the total. Whether this one's there or not, that pressure is assigned to helium. So A is the only one that, well, we found our right answer. And we don't have any wonky ones in there like 2 of the above or none of the above type of thing. You know, test taking technique. If we had any of those oddballs in there, we'd have to look at every one of them. But as it is, we found our answer. Right. Number 9. Which of the following is not a factor in determining the magnitude of the vapor pressure of a liquid? The magnitude of the vapor pressure of a liquid. All right, if we have a liquid in a container, say an Erlenmeyer flask, and it's stoppered, and we have the liquid down here. When it reaches equilibrium, there's going to be a pressure in here due to the evaporation of molecules from the liquid. And when it reaches equilibrium, the rate of evaporation equals the rate of condensation. Okay, that's what vapor pressure means. So what affects the movement of one direction or the other? One major factor is temperature. If you increase the temperature, you increase the vapor pressure. Okay, we know that. What other factor? Well, if it's the same liquid, nothing else affects it. But if we change the liquid, the nature of the molecules, the attraction that they have for one another. So attractive forces. Attractive force If it increases, then the pressure decreases. So let's see. Which factor determines the magnitude of the vapor pressure? All right. Temperature of the liquid, A. Yeah. Strength of the attractive forces between molecules, yeah. Size of the container, no. Oh, not a factor. Okay. Read the fine print. Because A and B are both factors. C, the size of the container. No. The size of the container does not matter as long as you still have some liquid there. Because if the container is so big that all the liquid evaporates, then you can't have an equilibrium. So that doesn't produce a vapor pressure that's valid. So I guess we could argue the size of the container might affect, it won't affect the vapor pressure, no. It'll affect the measured pressure, yes. Types of forces between molecules, yeah, that's another way of saying B. So the one that doesn't have an effect on the vapor pressure is C, size of the container. If you get a bigger container, then this volume is going to drop down lower before it reaches equilibrium. All right, number 10. A liquid is placed in a closed container, equilibrium is reached when? Okay, I already told you that one. When the rate of condensation equals the rate of evaporation. Right? It's all about the rates. So that's B. How about 11? Liquids will boil at lower temperatures at higher elevations because. What do we mean by boiling? When we say a liquid boils, or we measure the boiling point, what are we saying? We're saying that's the temperature that this liquid will produce vapor from its internal, right? Not at the surface anymore, but from internal. And it does that at a certain temperature and a certain pressure, atmospheric pressure, whatever is resisting the movement outside. If we decrease the pressure bearing down on a liquid, then it tends to evaporate more easily. Right? And if you can decrease the temperature, you can keep, say you put a container of water in a vacuum chamber. It's fun to watch. And you suck all the air out. And you don't do anything with the temperature. The temperature is the same as it is outside, like 20 degrees or 25 degrees, whatever, room temperature. You keep sucking the air out, and at some low pressure, that water will start to boil. Because the pressure is low enough now that the evaporation can occur from inside the liquid. There's enough energy in the liquid to form gas. So after saying all that, liquids will boil at lower temperatures at higher elevations because the vapor pressure which boiling occurs is lower. That's it. It's just that simple. 12 and 13. So if you're going to move to, I don't know, Denver, and you like your eggs hard boiled, right? It's going to take you longer to get there. Because when you start boiling water, it's going to boil at a lower temperature, right? And hard boiled eggs don't care what the pressure is. They only care what the temperature is. And the temperature of your boiling water is lower in Denver than it is here. Okay, 12. Which of the following statements about intermolecular forces is incorrect? All right. So it looks like they're all unique statements. We have to find the one that's incorrect. A says they must be overcome in order for molecules to escape from the liquid state in the vapor state. Yeah. Right. The intermolecular forces, because gases, in fact, ideal gases or gases that behave as if they were ideal, behave as if they're just billiard balls, right? They bang off each other and there are no intermolecular forces that attract them to one another. Now, we know that's not true, but it's close enough. So A is true. B says they are much weaker than intramolecular forces. Okay. Inter between molecules, intra within molecules. Is that true? The intermolecular forces are weaker than the intramolecular forces. Why, how do we know that? If it is true, why? How do we know? Well, if that were not true, you wouldn't have molecules, right? The intermolecular forces would rip everything apart, right? The intramolecular forces must be stronger in order to hold molecules together, right? So B is true. They are much weaker than intra. C, they are electrostatic in origin. Oh, yeah. Yeah. It's safe to say that. These attractive forces are electrostatic. They occur within molecules rather than between. No. Intra is within, inter is between. So D is your false one. In which of the following liquids would London forces be the predominant intermolecular forces? What are London? Actually, the correct terminology is London dispersion forces. London is the man who proposed it. Dispersion refers to the instantaneous movement of electrons in the molecule, or the atom for that matter. These are not permanent dislocations of electron density. These are temporary. So how are they on the scale of intermolecular forces? What's the strongest intermolecular force? Well, ion-ion, of course. Under that, we have dipoles. Or you can have dipole ion also. But within dipole, which is the highest level of attraction in dipoles? Remember that special group? Hydrogen bond. That's the strongest dipole-dipole. And then if you don't have access to dipoles, these are permanent dislocations of electrons. If you don't have that, then the next weakest one, and we're getting weaker as we go down, the next one are the London forces. So the London forces are always there. They're always there, whether these are there or not. If these are there, then they're so strong that London dispersion forces are too weak to matter. But if these are missing, then the London dispersion forces become important. The only way that attractions can occur. So what you want to look for are the choices in which you don't have ion-ion or dipole-dipole type interactions. So what do we do there? A, B, C, and D. How about this one? Does that one have a dipole? We drew Lewis structures, didn't we? Did we draw Lewis structures? Like that. Okay. These are about close to equal. So the main dipole forming bond is this one for the whole molecule. This one has a dipole interaction. How about this one? When we draw that one, perfectly balanced. It's 100% nonpolar, which means none of these work. It only has access to London. That's it. So we found our answer. H2S would look like water. And the last one, IF, would be this direction. Because fluorine has the largest electronegativity of all. Okay, so we found our answer. Nitrogen would be the one that's predominantly London dispersion forces. Okay, 14 and 15. Which of the following descriptions apply to matter in the solid state? Okay. Apply to matter in the solid state. Okay. Now, notice that D and E are the wonky ones. More than one correct response is D. No correct response is E. That means we have to look at A, B, and C, all three of them. So is A true? Definite shape and high density. Oh yeah. That's characteristic of solids. Cohesive forces dominate over disruptive. Oh yeah. Definitely. Kinetic energy dominates over potential energy. No. Potential energy dominates. So that one's false. But we do have more than one. So D would be your correct answer. Because you have more than one. $15. Which of the following samples of gas would have a new volume of 3 liters if the pressure is decreased from 3 to 1 atmosphere at constant temperature? Okay. What gas law are we looking at here? We got volume and we've got pressure. Talking about Boyle's law, aren't we? Right. Everything else held constant. Okay. Well, let's see. Initial and final. All right, what do we have here? Initial volume. Oh, a new volume of 3 liters. Final volume. Okay. Pressure is decreased from 3 to 1. 3 atmospheres to 1 atmosphere. Okay. Pressure and volume are inversely proportional. So if we take the pressure down by a factor of 3, we decrease the pressure by 3, we increase the volume by 3. So this one should be 1 liter. Okay. And it doesn't matter what gas it is. That's there to throw you off. Helium, carbon dioxide, hydrogen sulfide, doesn't matter. Gas laws pertain to all gases. So 1 liter of helium satisfies the conditions. Okay, which of the following is correct equation for the combined gas law? Oops, write the answer of it. Let's try the number. Okay, 16. Combined gas law. Right, notice that the authors prepared this question and it doesn't include moles. Right, when I presented it to you in class, I included moles. But now we're going to leave the moles out. So if we look at the combined gas law in the way we presented it earlier, pressure volume over temperature equals pressure volume over temperature. They're using ones and twos? Yeah. Okay. So each one of those solves for pressure 2, volume 2, temperature 2. One of these. Right? If we solve for pressure 2, that means that T2 goes on top over here, and V2 comes over here, like that. Right, so is that right? PV? No. A says T1 should be T2, right? So A's out. How about B? B solves for V2. Okay. V2, keep it over here. We still have P1, V1, and then T2. And then we're going to keep V2. That means P2 comes over here. So let's look at B. V2, P1, no. V1's right. P2 is wrong. Needs to be flipped. Right? So B is wrong. The reason I'm going to all this trouble is because suppose I get sneaky and I change things around. You can still solve the problem the same way, you just won't have the same answer. Right? Maybe I'll change something around and one of those will be right. So don't let your brain get lazy. T2. Right? We solve for T2. All right, now T2, let's do it this way. T2 is in the denominator over here, so we're going to bring it over to the numerator over there. That means that P2, V2, and then T1 comes over here. And then P1, V1 comes over there. So let's see. If that's T2, T1's correct for C. P2's correct. V2 is wrong, V1 is wrong, V2 is correct. So C is also wrong. None of them are right. All right, 17. When the vapor pressure of a liquid equals atmospheric pressure, the temperature of the liquid equals. Well, if it's 100 degrees C at sea level, it would have to be water, but it doesn't tell us what the liquid is, right? So we can't say that. A can't be it. The boiling point of the liquid. Actually, that's true. The vapor pressure of the liquid equals the atmospheric pressure. The temperature is the boiling point of the liquid. So B is correct. Look at C. The difference there is just one word, the normal boiling point of a liquid. The normal boiling point of a liquid occurs not just at whatever the pressure is, it occurs only at 1 atmosphere pressure. Okay. So if the question were when the vapor pressure of the liquid equals 1 atmosphere pressure, the temperature of the liquid is the normal boiling point of the liquid. It's that fine difference. But the way it's presented, B is the answer. '18. Intermolecular forces differ from intramolecular forces in that they occur only in liquids. No, they occur in solids. And actually, even though most gases behave ideally, they will still have some intermolecular forces. They'll just be very weak for gases. So A is false. They are much stronger. No, intra is the stronger one. So B is false. C says they occur only when hydrogen atoms are present. That's hydrogen bonding. That's alluding to hydrogen bonding. It's not a complete description, but that's the implication. But it's not true. Intermolecular forces occur all the time. More than one correct? No correct. There are no correct answers there. They're all false. Going to 19. All right. In which of the following pairs of molecules would the first listed member of the pair have a higher boiling point than the second listed member of the pair? So we're thinking about, all right, which ones would have, the first one in the pair would have the stronger intermolecular forces. And we're talking about, for instance, the first one would be hydrogen fluoride and hydrogen bromide. Right? If they're pure, they're pure substance, they're not mixed, they're just pure, comparing these two pures. The higher boiling point would be the first one. We're comparing HF and HBr. We want to look at the strength of the dipole for these molecules, right? Which one has a stronger dipole? Well, they're both going to be dipole that way. But which one should have the bigger arrow? I drew that one bigger, but actually this one is. Why? Because fluorine has a larger electronegativity, and they're both bound to hydrogen. Right? So it gives you a stronger dislocation of electron density in here. Also, fluorine is a smaller atom. Right? So it's going to be closer to hydrogen. And hydrogen, the bond itself is going to feel a stronger pull because of the proximity of the other atom to fluorine, whereas bromine is, by comparison, is huge. So we found our answer. So yeah, this one. If we look at the others, difluorine and dichlorine, those are both nonpolar. And actually, this would be a good point to make. If you're looking at that one compared to this one, no, chlorine, excuse me, chlorine. Which one has the stronger bond? First of all, that one right there. That one has the stronger bond. We would expect that this one to have the stronger bond, right? Because you can have it's just smaller atoms. You should be able to have more overlap of their orbitals to bring them closer together, give them that stronger bond, but you don't. Because these 9 protons versus these 17, these cannot get as close to each other as these can. Because once you start getting close together to overlap those orbitals, you have smaller atoms, and these protons, this nuclear charge, this positive nuclear charge repels. And it repels stronger than it would for something like this. So this one has the stronger bond. Which means, and if we draw the Lewis structure, right, well, they're both polar, but which one can have, if they're, nonpolar, if they're both nonpolar, what forces do they have available to them? Only London, right? Only London forces. So, and London forces are proportional to the size of the atom or the molecule. This is a bigger molecule, so London dispersion forces will be higher here, right? So it's in the wrong position. If this one were first, then that one would be a valid answer also. Okay. C, you got a nonpolar oxygen versus a polar nitrogen monoxide. So that's a no-brainer, right? It's reversed. It's in the wrong order. right? So if this one had been first, then we'd have more than one correct answer, and D would be correct. So that's all I would have to do for a test question. Just flip these around, and then it changes the answer from A to D. Would I be that sneaky? I might be. If I did, would I get out here alive? I may be old, but I can still run. 20. Characterize each of the three given statements as true or false, and then answer A, B, C, or D accordingly. All right, so we've got 1, 2, and 3. We got to decide how many of these are true. One says sublimation and deposition are opposite changes. What is sublimation? All right. Sublimation is solid to gas, correct? What's deposition? Gas to solid. They are opposites. So that one is true. 2, a pressure of 1 atmosphere is greater in magnitude than the pressure of 720 torr. All right, we can't compare apples and oranges. 1 atmosphere is how many torr? 760 torr. That is greater than 720 torr. Right? And a torr is a millimeter of mercury. So that one's true. How about 3? The boiling point of a liquid can be increased by heating the liquid to a higher temperature? No. You can get to the boiling point by heating it, but you can't change the boiling point by heating it. Right? So that was false. We do have 2, though. So B would be the correct answer. 2 of the 3 statements are true. We got another one. 21. All right. Associated with Charles' law is the concept that if the temperature of a gas increases, the volume of the gas increases. Is that true for Charles' law? Yeah, temperature and volume are directly proportional. How about liquids show little change in volume with changes in temperature? That's probably true. They will change some, but the key word there is little. Little change. And then 3, dipole-dipole interactions are examples of intramolecular forces, and hydrogen bonds are examples of, no, they're both examples of intermolecular forces. So that one's false. And 21 is B, 2 of the above. I think 22 is going to be another similar arrangement here. Okay. 1, 2, and 3. Both dipole-dipole interactions and hydrogen bonds are stronger than most single covalent bonds. No. That's another way of saying that intermolecular forces are stronger than intramolecular. And that's not, it's never true. That's false. The value of the ideal gas constant is the same for all gases under ordinary conditions of pressure, volume, and temperature. Yeah, that's true. Right. If your units are liter, atmospheres, and moles, and temperature K, that would be the value. And it's the same for any gas. Both condensation and freezing are endothermic changes of state. Condensation, all right? Condensation is what? Gas to liquid, right? gas to liquid. That's exothermic. All right, so we don't have to go any further. So see, only one of the statements is true. Just this one. See, we'll skip a few of those. They take a lot of time to do. 25 then. Let's see, 1, 2, and 3. Water's boiling point is much lower than expected based on comparison with other substances because of hydrogen bonding. Well, the part about hydrogen bonding is true. Based on comparisons of other substances because of hydrogen bonding, yeah. But water's boiling point is much higher than expected, right? It ought to be, if it followed the pattern of other hydrides like sulfur, hydrogen sulfide, hydrogen selenide, hydrogen telluride, then if it followed the pattern, then water should be below zero. Right? But it's not. For that reason, hydrogen bonding. So the statement as given is false. Number 2, in the gaseous state, disruptive forces and cohesive forces are about the same magnitude. No, that's a liquid state. They're about the same. Gaseous state, the disruptive forces are much greater than the cohesive forces. So that one is also false. And 3, as liquid surface area increases, the rate of evaporation of a liquid increases because molecules encounter less external pressure. Okay, the first part of that statement is true. The rate increases, but not because of less external pressure. It's simply because of more surface area. So they're all false. Right? That's D. None of them are true. 26. One, 2, and 3. Oh, no. All right, we're back to the real world, normal questions. For each of the physical state characterizations, select from the response list the physical state or states to which characterizations apply. Okay, indefinite shape. Indefinite shape. Which phase would satisfy that condition? Liquid? How about gas? Yeah. Gas also, liquid and gas. Solid has a definite shape, but these two don't. So D, gas and liquid. All right? That would be the correct answer. How about if I picked one of these others? How about 27, definite volume? Solids and liquids. Okay. How about 28? Potential energy dominates over kinetic energy. That would be a solid only. Right? 28, solid. Potential energy dominates over kinetic energy. That doesn't mean that solid molecules don't have kinetic energy. They just don't have enough to overcome the cohesive forces. 29. When does a material have no kinetic energy whatsoever? Absolute zero. Once you get down to that point, our classical understanding kind of falls apart. You have to go to some quantum mechanical oddballs, and you can get, well, I'm not going to waste your time with those details. You get some funny things happening at that level. All right. 29. I've got it up there already. Let's see. Particles are relatively close together. That occurs in both solids and liquids. These are fixed in position. These are not, but they're still close together. So solids and liquids satisfy that condition for 29. All right, 30. Consider the mathematical expression for gas laws listed. Select the correct name. Okay. P1V1 equals P2V2. That's Boyle, maybe. Boyle's law. 31. Volume and temperature. Is it written correctly? Yeah, V1 over T1 equals V2 over T2. Remember, whenever you have two variables in a quotient relationship, they're directly proportional. If they're equal to a constant. If they're a product, then they're inversely proportional. So this is definitely Charles' law. Let's see, skip that. How about 34? Considering change of state description, select the name of the change of state for when energy is absorbed. Energy is absorbed when you go from a more compact state to a more diffuse state. So if you go from a gas to no. When you go from a liquid to a gas, you have to absorb energy. If you go from a solid to a liquid, you have to absorb energy. Or if you go from a solid to a gas, you have to absorb energy. This one is called what? Liquid to gas is vaporization, boiling. Let's call it boiling. Now let's call it vaporization. That would be more accurate because it doesn't have to boil. Vaporization or evaporation. That's probably a better term. Solid to liquid, melting. Solid to gas, we did that one earlier. Sublimation. So are any of these in there? Yeah, sublimation right there. A. Condensation, deposition, freezing. Those are all exothermic processes. They have to give up energy in order to accomplish that phase transition. 36. This one's starting to get a little weak. Characterize the effect that changes will have on the vapor pressure and boiling point of a liquid by decreasing the temperature of the liquid by 20 degrees at constant pressure. Okay. If we decrease the temperature by 20 degrees, what effect will it have on the vapor pressure and boiling point? Okay. Vapor pressure. We decrease the temperature, the vapor pressure is going to go down. Right? How about the boiling point? Boiling point. No change. So decrease vapor pressure, no change boiling point. Let's see, A, B, B. B fits. Okay. Time. Okay, we've used up an hour. 38. For the following intermolecular force descriptions, select the correct name for the response from the response list. Okay, so which one of these is permanent electrostatic interaction between polar molecules in which no hydrogen is present? Okay, if it's permanent, it's either ionic or dipole or a combination. Right? It's not London, no hydrogen present, so it's not hydrogen bonding. It's not a covalent bond, right? Covalent bonds are sharing electrons. So D, the dipole-dipole interaction, is the only one that fits. Let's see. 40. A solution may contain what? All right, these are definitions. A solution is made up of solvent and solute. How many of each? One only. Many if you desire. So only one solvent, many solutes. A would be the correct answer. Okay. 41. We must be into chapter 8, solutions. Which of the following statements concerning a saturated solution is incorrect? Okay, what do we mean by a saturated solution? At a given temperature, a saturated solution contains a maximum concentration of solute. Okay, so incorrect. Undissolved solute must be present. Is that true? The key word there is must. It may be present, but it doesn't have to be. Right? I can prepare a saturated solution of, say, sodium chloride, and I can have some solid sodium chloride in the bottom. So how did I get there? Well, I looked up the solubility of sodium chloride, and I took a certain amount of water, and I took the amount of salt that would saturate that amount of water, and then I added maybe 10% more. Then I put them in there, stirred it, heated it. All of it goes into solution. Then I set it on the desktop and let it cool. Now, maybe it becomes super saturated, and all I have to do to make it saturated is either drop a crystal of sodium chloride in there or scratch the inside of the beaker and then wait. And eventually I'll have a saturated solution and precipitated sodium chloride that won't dissolve. Then if I want to set up the A situation, well, no, the opposite of the A situation, where there's no undissolved solute present, I just filter it. And as long as I don't change the temperature, it's still saturated, but there's no undissolved solute. So A is false and satisfies the conditions. If we look at the others, undissolved solute may or may not be present. That's correct. C says undissolved solute, if present, is continually dissolving. Yeah, that's true. There's an equilibrium set up. Right? If you've got solid in the bottom and it's saturated, then you're going to have that solid dissolving, but you're going to have the solute precipitating at the same time at the same rate. If present is an equilibrium with the dissolved solute, that's another way of saying that. So the one that's false is A. Doesn't have to be present. 43. For which of the following types of ionic compounds are most examples insoluble in water? All right. Let's see. Yeah, you do have a copy. You'll have a periodic table and the solubility chart will be in the test. Right. So you can just look at the solubility chart and see, look at the nitrates, right? Find the nitrates on the left-hand side and go across there. They're all clear. All nitrates are soluble. Sulfates. How about sulfates? Go down to sulfates. SO4. SO4, 2 minus. Some of them are soluble, some of them are insoluble. Most examples, insoluble. Now, there's about even number according to that chart. How about hydroxides? Most, let's see, are most examples insoluble. So hydroxide, let's find hydroxide. There it is. Go across there. Sodium and potassium and barium are the only soluble hydroxides out of all that list. So the hydroxides would satisfy, right? Most of them are insoluble. Chlorides are mostly soluble with 3 exceptions, right? Silver, lead, mercury. So the answer is hydroxides. Most are insoluble. All right, 45. What is the molarity of a solution containing 16.7 grams of ammonia? And 1.5 liters of solution. So the volume of the solution is 1.5 liters. How do we calculate molarity? Moles per unit volume, and the volume has to be in liters. Okay? So that's already met. We got the volume in liters. That's not moles. So how do you convert that to moles? Not a clue, right? Try dimensional analysis. We're at grams, 16.7 grams. We want to be moles. All right, so how do you get there? You need a conversion factor. Cancel grams, denominator, numerator, and leave you with moles. If you see grams and moles in a quotient relationship, always think molar mass. So what's the molar mass of ammonia? Well, let's see. Nitrogen is what? 14.01, I think. Yeah, 14.01. And hydrogen is 1.01 times 3. 407, 1704. Right. So we know the value is going to be less than 1. And I got the wrong answer. That's more like it. 0.980 moles. This Band-Aid off here. Okay, so now we can put things in the proper position. 980. Yeah, 3 significant figures. that's moles, and 1.5 liter. And I get 0.653365 molar. But we've only got two significant figures. 0.65 molar. And the best answer is 0.653. But they should have, where did I mess up? Oh, I did. There's a zero there. Okay. There we go. My fault. All right. 46. If 145 milliliters of 2 molar KOH is diluted to 1.15 liters, the resulting solution contains how many moles of KOH? All right. What kind of problem is this? A dilution problem. And what can we use to calculate the end product of a dilution? We can use the molarity of the concentrated, volume of the concentrated equals the molarity of the dilute, volume of the dilute. All right. So what's the molarity of the concentrated one? 2 molar? What's the volume? 145 milliliters. Okay. What's the molarity? We don't know. That's unknown. And the volume of the dilute is 1.15 liters. But we use milliliters here. So how many milliliters is 1.15 liters? Move the decimal place 3 to the right. Okay, so now we can find the molarity, but you know what? The resulting solution contains a certain number of moles of KOH. We don't need to go this route. Because what is this going to tell us? If molarity equals moles per unit volume, then moles equals molarity times volume. We got that right here, don't we? We don't have to go the whole dilution route. But the answer is in moles. So in order to get, this is going to give us millimoles, right? So if we use 0.145 times 2, then we get 0.290 mole of KOH, right? Hey, I was making it harder than it needed to be. We could do that, but that wasn't the question. That was the question. All right, let's see. 47, a colloidal dispersion differs from a suspension in that colloidal particles what? What's the main difference between a suspension and a colloid? In a colloid, the particles don't settle. It's not a solution, but the particles are so small that the kinetic energy of the dispersing medium is enough to keep those particles suspended. Right? Like a fog. That's a colloid. So which one answers that? Colloidal dispersion differs from a suspension in that the colloidal particles are large enough to scatter light. Well, yeah, that too. What do we call that? in the laboratory setting. We call that the Tyndall effect, where you can shine a light through a solution and you can't see it go through the solution. But if you shine it through a colloid, you can see that light beam because the particles are big enough to scatter the light beam as it travels through. It's easier to see with a laser, but I don't carry a laser with me. I carry a pen light, which works pretty good. Let's see. So B is the correct answer. Large enough to scatter light. 48. Compared to pure water, 1 molar sugar water solution will have what? Okay. Here we have colligative property. And it looks like we're looking at two different colligative properties. Boiling point elevation versus, and the other one is freezing point depression. Right? The boiling point will increase as we increase the molality of the solute, and the freezing point will decrease as we increase the molality of the solute. That's the one we're going to work with today in the lab. So which one satisfies? Oh, and vapor pressure. Let's see. Vapor pressure. If we add, that's Rayleigh law. The vapor pressure will, let's see. Rayleigh's law says the actual pressure equals the mole fraction of the solvent times its standard vapor pressure. So a 1 molar sugar water solution, and the solute must be non-volatile. If it's volatile, then we get a modified Rayleigh's law, and we didn't do that. We haven't gone that far. So sugar is non-volatile. So with a lot of sugar, what do we get to the, well, it's got all three of them. What happens to the vapor pressure? We increase the amount of sugar. What does that do to the mole fraction of the solvent? It goes down, right? Because you have to add the mole fractions of both of them together equals 1. So this goes down. That means this value is going to go down. Okay? Freezing point. It should decrease also with an increased solute. And boiling point will go up. So which one? Let's see. Vapor pressure's first. Vapor pressure decreases. So A, C, or D would work. At least for the first one. Boiling point should increase. So C is the only one with a higher boiling point. I think we found our answer. We can do the other part of it to check. Lower freezing point? Yep. So C is the correct answer for that one. You have to know the effect of a dissolved, the solute, the effect of that solute on the colligative properties in order to answer the question. Now, which colligative property did we leave out in that one? There's another one. Right. Remember the giant sequoia tree we talked about? Osmotic pressure. Okay. All right. 49. What's the freezing point for a solution containing 1 mole of sodium chloride? So we got 1 mole of sodium chloride dissolved in 1 kilogram of water. 1 kilogram of water. Okay. And we want to know the freezing point. All right. Can we calculate that? Yeah. All we need is the correct formula. So the change in temperature for the freezing point is equal to what? Well, we've got a constant for the freezing point of water, which is 1.86. It's not given in the problem. It should have been put in there. 1.86. And then we have the Van Hoff correction and the molality. So what's the molality here? 1 mole per kilogram. So that's, molality is 1 molal, 1 mole per kilogram. And I is 2, because this breaks up into 2 ions. Okay? And molality is also moles per kilogram. This would be degrees C per molal, or we could say degrees C per degree C kilogram per mole. Either way works. That's what molal means. So this cancels that, leaves us with degrees C, and 2 times 2.86 is 3.72. So the change in temperature, the absolute change of temperature, is 3.72 degrees C. And if it's a freezing point depression, that means it's that much below the freezing point, which is below 0. So the temperature is actually 3.72, minus 3.72. Now, some textbooks and reference manuals for the freezing point constant will put a negative sign here. So it guarantees that the change is going to show up as negative here. So don't let that throw you. Otherwise, you understand that the difference in temperature is a depression. And then you subtract that from the freezing point of the pure substance, and you get your actual freezing point. All right, number 50. Crenation of red blood cells occur when the cells are placed in what? Hypotonic, isotonic, hypertonic. Physiological saline is the same thing as isotonic. So B and D. The cells will be perfectly happy in an isotonic solution, right? No adverse effects. A hypotonic solution means the concentration of solute is less outside, or the concentration of water is greater outside. Right? The hypotonic solution. So that means which way is water moving? Into the cell. If the hypertonic solution is outside the cell, then it has a lower concentration of water, higher concentration of solute than in the cell. So with the water less outside than it is inside, the water is going to move through the membrane out and give you crenation. So C is the answer. A hypertonic solution will cause crenation. #51. Which of the following solutions is hypertonic with respect to blood? All right, we've got 2 types of measurements here, mass, volume, percent. So what's isotonic? That's our midpoint. Sodium chloride is isotonic at 0.9% mass volume. How about sucrose? Or glucose, excuse me. Remember, D5W, which is dextrose, 5% weight volume. Okay? So we're looking for hypertonic. That is a higher concentration than either one of these. All right, 0.5 is less, 0.7 is less, so the sodium chloride doesn't work. 4.5 is less, 7.6 is greater. That's hypertonic. So D would be the answer. Let's see, 52. Let's see, which of the following statements about solutions is correct? A solution. Okay, we got more than one or no correct. So if we look at A, B, and C, A, B, and C, a solution is a homogeneous mixture. Oh, yeah, that's true. B, it is possible to have solutions in which both solute and solvent are solids. Yeah, that's true. Like brass or any alloy. Let's see. C, solutions readily separate into solute and solvent if left undisturbed. Nope. That's characteristic of solutions is they do not separate under any circumstances. All right, so D is the answer. We did have two correct ones. 53. Crystal of solid sodium chloride is placed into an aqueous sodium chloride solution. Okay, sometimes pictures work. So we got a solution here of sodium chloride. And we drop a crystal in here of solid sodium chloride. It's observed that most, but not all, of the crystal dissolves. Right? Some of it dissolves, so we see it shrink. And some of it goes into solution. But it stops. So when does it stop? When the solution is saturated. Okay. But this means the original solution was unsaturated. If some of this dissolves, that means it had to be unsaturated when we put it in there. Now it's saturated after sitting there for a while. All right, so only B is correct. 54. How many questions I got in this one? I don't know if I'm going to have enough time. Okay, I think we'll have enough time. 54. Consider the following substances and their polarities. Okay, A is polar. A is polar. B is polar. C is nonpolar. And D is nonpolar. Okay. It is true that what? Which one's soluble in which? These two are soluble in one another. These two are soluble in one another. These are not. And that way, or this way, they're not soluble. Okay? Only the polar, nonpolar, and polar are soluble. So which one satisfies? Let's see, A is more soluble in C than B. No, A is more soluble in B. So A is false. B, C is more soluble in D than A. Yeah, that's true. B is true. And C, D is more soluble in B. Nope, it's more soluble in C. All right, so we only have one right answer, and that's B. Okay? That's the rule of thumb. Like dissolves like. And what we mean by like is polarity. 55. In which of the following sets of ionic compounds are all members of the set insoluble in water? Okay, so in order to answer that question, you need to go to your solubility chart. And if you don't already know, we want all insoluble. A, silver chloride and lead 2 chloride are insoluble, but ammonium chloride is soluble. All right, so A is not it. B, carbonates. Most of the carbonates are insoluble. All right, we look at carbonate. Where is it? Here it is, carbonates. The only soluble carbonates are sodium, potassium, and ammonium. And those are not there. So B, all of those are insoluble. All the carbonates are insoluble. How about sulfates? Lead, iron, barium. Okay, go down to sulfates. Lead is insoluble. Iron is insoluble, and barium. Where's barium? There it is, barium. Wait a minute. Sulfates. Oh, I was looking at the wrong list. Sulfates. There we go, sulfate. Iron is soluble. Barium sulfate is soluble. Iron sulfate is soluble. Barium is insoluble. Okay, so that doesn't work. I should have known that. Have you ever had a barium enema or an X-ray of your colon? No, they say it's not that fun. But they use barium sulfate because it's insoluble. Barium is a huge atom. See down there, period 6. Barium is a huge atom, and it absorbs X-rays really good. Really, really sucks them up. So it's a good contrast. And they use barium sulfate because it's insoluble, right? They can pump that stuff into your colon, and then when they're done with it, you can expel it, and none of it dissolves in your system. So there's no toxicity effect. All right, so the answer is B. All 3 of those are insoluble. And let's see, 61, 2, and 3. 61. Which of the following solutions has an osmolarity of 3? Osmol 3. Okay. Well, let's see. What is osmol? Osmol is a derivative of molarity, which takes into account the dissociation of the solute. Right? If the solute does not dissociate, then molarity and osmolarity are identical. That means A is 4 osmol, right? Because glucose does not dissociate. B, 2 molar sodium chloride yields 4 osmol because it breaks into 2 ions and gives you twice the osmotic potential. How about C? 1 molar, what is that? Sodium phosphate. Sodium phosphate. Is that correct? Yeah. 3 minus, 1 plus. So we need 3 of these to balance that one. Okay, this produces 4 ions, which also yields 4 osmol. None of them are 3. Right? They're all 4. So all I would have to do is change osmolarity to 4. And then the answer would be, instead of E, it would be D. Right? Think in those terms. How sneaky could your instructor be? All right, 62. In which of the following pairings are the terms closely related? All right, hemolysis. What's hemolysis? Lysis means to break or cut. So, and heme is blood. So your red blood cells will break apart under pressure if water is taken in. That's in a hypotonic solution. Yeah. So that's true. Hemolysis and hypotonic solution go together. How about B? Hypertonic, higher osmotic pressure than within cells. That's also true. Remember, osmotic pressure is measured when you have the solution inside your tube and a membrane, and then pure solvent on the outside. Pure solvent's going to move in until the height of that hypertonic solution reaches a point where its pressure is driving water to return at the same rate it's coming through the membrane the other direction. Okay. So when we say the osmotic pressure is higher for hypertonic solutions, that is true. That's always true. C, isotonic solution crenation. Nope. Those cells are perfectly happy. They're not going to change their shape at all in an isotonic solution. But more than one is correct. Right, these two. All right, 63. Oh, another one of those. All right, so we have 1, 2, and 3. Equal volumes of two solutions of the same molarity contain the same number of grams of solute. Is that true? Same number of moles, but not the same number of grams necessarily. Right. So that one's false. Let's see, 2. Hemolysis and crenation are opposite processes. Yep. And 3, the solubility rule, like dissolves like, is not adequate for predicting the solubility of ionic compounds in water. That is true. Because some ionic compounds are more soluble as the temperature increases, and some are less soluble as the temperature increases. So yeah, that like dissolves like doesn't predict that for us. So 2 are, since it's not adequate, yeah. 2 and 3 are correct. So 2 of the 3 statements are true. 65. One, 2, and 3. Addition of 40 milliliters of water to 10 milliliters of 8 molar sodium hydroxide produces a 2 molar sodium hydroxide solution. All right, if we're, we have 10 milliliters of 8 molar, 10 milliliters of 8 molar, and they're saying that 40 milliliters, addition of 40 milliliters. So the volume now is 50 milliliters, correct? Should produce a 2 molar solution. Let's see if that's correct. 2 times 50 is 100, right? 8 times 10 is 80. Nope, that's false. Not work. Henry's law is a pressure solubility relationship for gases and liquids. Yeah. The higher the pressure of the gas over the surface of the liquid, the more concentrated it is in the liquid. More of it dissolves in the liquid. Boiling points are the basis for the solubility rule, like dissolves like. No, polarity is the basis for like dissolves like, not boiling points. They may be related, but the rule of thumb, like dissolves like, is based entirely upon polarity. So only one of those is true. That's C. 66. Let's see. How's our water doing? Our water's, yeah, it should warm up pretty quick. Let's see, 66. 1, 2, and 3. Number 1, 2 liters of 6 molar solution would contain 12 moles of solute independently of the density of the solute. Volume times molarity is moles. So 2 times 6 is 12, 12 moles. That's true. Right? For liquid-liquid solutions, volume of the solution is always greater than the sum of the volumes of the solute and solvent because of solute-solvent repulsion effects. Not always. Sometimes the volume is less after the solution is formed. Sometimes it's more. So that one's false. As a blanket statement, 2 is not true. 3, osmotic pressure is the amount of pressure needed to prevent the process of osmosis from occurring. That's one way of putting it, right? As the level of that hypertonic solution rises, then the pressure on the membrane increases, and then at a certain point, osmosis stops. So that's another way of putting it. Osmotic pressure is the amount of pressure needed to prevent the process of osmosis from occurring. That's true. That's true. 2 of them are true. Okay, 67. For the set of ionic compounds, sodium nitrate, potassium nitrate, ammonium nitrate, choose the correct characterization of their solubilities in water from the response list. You can look those up, right? If you look up, just look up nitrates and follow it across, all of them are soluble. That's one of the rules, right? If you were headed for a chemistry degree, I'd have you memorize the rules. But since you're not, then I give you the chart. But one of the rules is all nitrates are soluble, period. So all 3 salts are soluble, right? In addition, all alkali metals are soluble, sodium, potassium, and all ammonium salts are soluble. So you're hitting it from both sides. These guys are perfectly soluble up to a point, and that point would be saturation. Right? Every salt has a saturation point or a solubility amount. 68. For these compounds, lithium chloride, silver chloride, magnesium chloride, choose the correct characterization of their solubilities in water. Well, I know silver chloride is not soluble. Lithium is an alkali metal, so it's soluble. Magnesium is also soluble, I'm pretty sure. Most chlorides are soluble. Chloride, here we go, chlorides, except for silver, mercury, and lead. So only 2 of those are soluble. B is the answer. 2 of them are soluble. 1, silver chloride is insoluble. Right. 80. I'll be getting close to the end. Using the response list, characterize the osmotic pressure for a 0.80 mass volume magnesium chloride. Okay, 0.8% magnesium chloride mass volume. Right. Is that isotonic, hypertonic, or hypotonic? Well, our comparison is this one, percent sodium chloride. You know what? That's not a good question. Because mass comparisons don't work between, see, sodium is a lighter atom than magnesium. If you just look at it as mass percent, then this is going to be a higher molarity. Well, maybe not, because magnesium is heavier. That question's bad. We're expecting it to be hypertonic, simply because this one has an extra chloride in it. So it would push this above 0.9 by comparison. All right. I hope I didn't put that in the test. If I did, I might just give you credit for it no matter what your answer is. All right, because the only way to actually compare them is to say, what is this molarity? Then what is this molarity? Osmolarity, right? Then you could do a fair comparison. But mass volume, no, because magnesium is heavier than sodium. Not a whole lot, just a little bit. So that's it.